In this project, we look at a fog-based solution to addressing one of the fundamental challenges of robot motion planning, finding enough compute time to address complex motion planning problems quickly. Consider, for example, a fetch manipulator robot that is tasked with cleaning up an office space or home. As it moves around the office, it needs to compute a three-dimensional motion planning problem, potentially for long navigation problems. This is typically easily within the capabilities of the robot's onboard CPU. On the other hand, when it gets to a location and needs to manipulate the environment, the short high-dimensional problem can require a lot of computing power. This is because the complexity of motion planning problems typically grows exponentially in the degrees of freedom of the problem. The navigation is a 3D problem, while the manipulation problem in this case has 8 degrees of freedom. In this scenario, and many like it, the motion planning compute requirements vary dramatically over time and from problem to problem. This can be due to changing environments, tasks, and dimensionality of the problem. One way to get enough computing power is to have an always-on high-end computer, either locally or in the cloud. Due to the sporadic requirements of motion planning, this is likely to be an inefficient use of resources. We note that there has been a wealth of related work in cloud-based motion planning. However, to the best of our knowledge, none of these look at serverless cloud-based computing as a potential cost-effective way of addressing sporadic computational demands of motion planning. So what is serverless Lambda computing? Serverless computing environments allow for the execution of small single-function operations, or Lambdas. Unlike other offerings that are billed in units of hours, months, or even years, serverless computing is billed in increments of 100 milliseconds. In this case, we propose a serverless Lambda that takes as input a motion planning problem and outputs a motion planning solution. But serverless computing comes with limits, including they do not allow inbound connections, though outbound ones are okay. They cannot store state from one execution to the next. They are typically time-limited on the order of tens of minutes, and they have limited multiprocessing capabilities. For example, Amazon's Lambda service offers at most 2 hardware threads for each Lambda, though this may change in the future. This, however, presents a problem. If we wish to use Lambdas to improve motion planning compute time, we need more computing than the robot has on board. As it is, one Lambda's computing capabilities is likely to be equivalent to a robot's onboard computing capabilities. So while one multi-core Lambda may be too slow for a motion planning problem, we propose using multiple multi-core Lambdas working in parallel to compute a single motion planning problem quickly. The architecture we propose starts with the robot requesting a service provider execute some amount of motion planning Lambdas in parallel. This would result in the concurrent execution of many Lambdas. However, in order to speed up computation of motion plans, these Lambdas will need to communicate with each other. And as mentioned, one of the limitations of Lambdas is that they cannot accept inbound connections. So we propose introducing a small coordinating server to facilitate communication between Lambdas. The robot, if it could receive inbound connections, could also act as a coordinator. With the coordinator in place, now the coordinator starts the Lambdas and tells each Lambda of its own IP address. Using that IP address, the Lambdas now open connections to the coordinator and can communicate with each other via the coordinator. Putting this together to address the motion planning problem, we present 2 approaches based on sampling-based motion planning. The first motion planning approach is based on the PRRT, which operates by generating random samples and connecting them into a graph. When samples are in collision, the planner rejects the sample and moves on to the next sample. The same applies for when samples cannot be connected to the graph without collision. Visually, in operation, the RRT looks like this. Extending from a start point, it samples and extends a tree while never going into collision with an obstacle until it reaches the goal. This planner is probabilistically complete, meaning that given enough compute time, it will find a solution with probability 1. Many have explored parallelizing the operation of RRTs, either by distributing between multiple processes or building a single shared tree. We propose combining a multi-core shared memory parallel motion planner, PRRT, with a distributed memory parallel motion planner, PRRT-OR. PRRT exploits parallelism within each Lambda, and PRRT-OR exploits parallelism of multiple Lambdas. With the proposed algorithm, multiple multi-core Lambdas compute a solution simultaneously, stopping as soon as any Lambda finds a solution. Executing on more lambdas simultaneously probabilistically decreases the expected time to find a solution. We also propose addressing asymptotically optimal motion planning using a variant of RRT star. RRT star operates much like RRT, but has an additional step of rewiring the graph towards optimality as it goes. Additionally, C-Forest and BitStar motion planners proposed that asymptotically optimal motion planners can be sped up by only considering samples that can improve upon the best path. Here we show a region in which samples can optimize the motion. With this addition, the motion planner quickly rejects samples that cannot improve the best path, speeding up overall motion planning. For asymptotically optimal motion planning using lambdas, we propose a combination of PRRT star and C-Forest. PRRT star efficiently exploits multi-core parallelism within each lambda, while C-Forest coordinates between multiple lambdas by sharing the best path information. In operation, as soon as one of the PRRT star lambdas finds a solution, it shares it with all other running lambdas. These lambdas then incorporate it into their planning, resulting in overall speedup of motion planning. This speedup improves with more lambdas computing. Here we show 15. And continues to speed up with even more lambdas. Here we show 100. We experiment with OMPL rigid body motion planning scenarios. These are the results for the cubicle scenario running the probabilistically-complete motion planner. On the x-axis is wall clock time. On the y-axis is the empirical probability of finding a solution by that time. The plot shows 1, 4, and 16 lambdas, with dotted lines showing single-threaded lambdas and solid lines showing two-threaded lambdas. We observe that increasing the number of concurrent lambdas shortens the time to find a solution. Similarly, we observe that there is a significant benefit of using 2 threads in each lambda instead of 1. We note that in Amazon's offering, each lambda has 2 hardware threads available, and it is the same price whether each lambda uses 1 thread or 2. Here we show the results for the twisty-cool scenario, observing a similar trend. We can also see more clearly the benefit of 2-threaded lambdas, as the 4 lambdas with 2 threads each, the green solid line, solves at about the same rate as 16 lambdas with 1 thread each, the orange dotted line. Here we show the results for the home scenario and for the apartment scenario. Now we present the results for the asymptotically optimal motion planning. As with prior graphs, the x-axis is the wall clock time. However, the y-axis is now the path cost. As this is an asymptotically optimal motion planner, the path cost shrinks over time. With these experiments, we went up to 100 lambdas, with the blue line showing the 100 lambdas. In this example and in the next, we can see a clear advantage to scaling capabilities of serverless lambda-based motion planning, with 100 lambdas being able to produce path costs in a fraction of the time that 1 lambda can in the same amount of time. We similarly see a clear advantage of exploiting the multi-core parallelism within each lambda. Here we can see that 16 lambdas with 2 threads each produces path cost approximately equivalent to 100 lambdas with 1 thread each. And here is the apartment. We now revisit the scenario we imagined at the start of the presentation, a fetch robot navigating and decluttering an office space. Here the fetch robot has approached the desk and will move its manipulator arm to grasp the bottle. Here we show the results of asymptotically optimal motion planning computed over 10 seconds while varying the amount of concurrent lambdas. No path smoothing was applied to the resulting motion plan. Here we see that the motion computed using 100 lambdas completes the task well before the motion computed using 10 lambdas. With 1 lambda and 10 seconds of computing, however, the motion planner was not able to find a solution. We have encountered some issues, however. The coordinator, whether on the robot or in the cloud, is a bottleneck on scaling. We have tested up to 100 lambdas, but to get to 1,000 lambdas, we are exploring new approaches to communicate between them. We have also observed that Amazon provides no guarantee on startup latency. This does not seem to have an impact on our experiments, but is a lingering concern. In conclusion, we have seen that multiple lambdas in a cloud-based environment can rapidly scale motion planning. This may prove to be a cost-effective solution, especially when compute requirements are sporadic. We are actively working on extensions to this project and would welcome ideas for collaboration. We hope you will check out our paper and project website and contact the authors if interested. Thank you.